Before we start computing eigenvalues, we're going to ask the question about how well conditioned that problem is. So in other words, how sensitive are the results? In this case, we think of the data to this problem as the square matrix A, and the solution would be the eigenvalues, the set of eigenvalues. We could look at eigenvectors too, but it gets more complicated. So we're just going to look at how the eigenvalues respond. So one way of asking that question is, suppose we take the matrix A and we perturb it by another matrix E. We add E to it. How does that change the eigenvalues? So one thing you'll notice is that this question is about absolute perturbations, not relative. And again, that's just to make the questions and the statements a little easier. Okay, before we get to there, we need one simple definition. So let's suppose that z is a complex number and t is some set of complex numbers. Then we want to define the distance. Oops. We define the distance from the point z to the set t as follows. So it's the minimum over all points w in t of the distance between z and w. Okay, so remember that in complex numbers, the magnitude of the difference of two complex numbers is as good as the distance between those two numbers. It's the same thing. And so we're just looking at the distance to the closest point in t. So if t were to be some blob of complex numbers, and z were to be the point outside, then the distance would be the distance given to the nearest point in t. So we call this quantity the distance dist from z to t. Okay, so that's a pretty natural definition. With that definition, we can state our main result, which isn't too hard to prove. It's in the book, but it's a number of steps, so I'm going to leave it out here. So suppose A is some diagonalizable matrix. So we have it in terms of a matrix of eigenvectors V and a matrix of diagonal matrix of eigenvalues D. Okay, and then we just write the eigenvalues as the set capital lambda. So capital lambda in this case is just the set lambda 1, lambda 2, and so on, up to lambda n. Okay, so now if mu, this is the Greek letter mu, if mu is an eigenvalue of the perturbed matrix, A plus E, then what we can say is that the distance from mu to the original set of eigenvalues is bounded by the condition number of the eigenvectors times the norm of the perturbation to A. All right, so the change in the eigenvalues is governed by the size of the perturbation we make, that makes sense, times a factor which can amplify it, and that's the condition number of the eigenvectors. Now remember that for any matrix, its condition number is at least 1. So the best we can do in this bound is if this condition number term here is 1, okay, which says that the change to the eigenvalues is bounded by the change to the original matrix. That's pretty nice. And when that happens, that means it only happens actually when V is an orthogonal matrix, as it turns out. And in that case, we say A is a normal matrix. So the picture for the normal matrix looks like this. We have some set of eigenvalues originally. Okay. If we perturb by, let's say, a small matrix, a matrix whose norm is small, call it epsilon, and then we draw little circles of radius epsilon around each eigenvalue. Then the eigenvalues of A plus E are going to be found inside these disks. So that's pretty handy. It kind of says that things don't change any more than you've changed the data to the problem. On the other hand, if the matrix is not normal and the condition number of that eigenvector basis is much larger than 1, then the eigenvalues might be very sensitive. So the cartoon in this case, if we start with those 3 eigenvalues again, in this case, even for the same value of epsilon, we might find that you get some set which is just some big blob containing these things. And the eigenvalues might be found anywhere inside that blob. So when you get the normal case, and again, normal means a technical thing. A is a normal matrix. And in this case, we have the non-normal case. And the perturbations to the eigenvalues can be much larger.